All right, we're going to start parallel circuits, which is found in module 5. So module 5, parallel circuits. Here's your PowerPoints. So the first PowerPoint that we used from the textbook actually covers parallel and series. So I'm probably going to go back and touch on that one first, and then we'll pick up on this other one. So what's the difference in a parallel circuit versus a series circuit? Actually, it's most of the stuff that we're going to work with is going to have parallel circuits or parallel loads, so things that are parallel. That means they each get their own supply. So there's more than one path for electrons to flow, and each one is independent of the others. Now they have the same power supply, but they can do with it as they need to. So if you have light bulbs in a series and you unhook one light bulb, then all the bulbs go out as a result. But if you have light bulbs in parallel, then if one goes out, the others will still light. So that's kind of the the analogy there, the difference there that you'll see in lab. That those things can operate separately. So how does that apply to HVAC? Well, you've got an outdoor unit that uses the same power to supply a condensing fan motor and a compressor, for example. Both of those run off of the same circuit, actually run off of the same components, but they have different controls that make them come on at different times or however they're supposed to come on. So let's go to the next part. So this is an example of, and this is actually just 4 loads, 120 volts, just showing you the difference between the 2 legs. So you'll notice you've got leg 1, 2, 3, 4. You have 4 different tiers to your ladder. If I was drawing this, I would actually draw it up and down, but they show this sideways for whatever reason. So you've got a light bulb, a fan motor, a compressor, and a heater. Notice how they just draw most of these loads as a circle, and then the heaters, they kind of draw that as a little zigzag line. So it's kind of a common symbol for that. So a lot of these loads, you're just going to signify them by a circle to say it's a load, maybe label it. And then later on, as we learn more about symbols and that kind of stuff, we may change those up a little bit. So here's more how I would draw one. So an application, here's a circuit that is would be kind of similar to what you'd run into on an outdoor unit. A little bit different, but still similar. So in this case, these are actually L1 and L2, which is high voltage, 240 volts, most likely. So you'll notice that we're bringing in some extra components at this point. So we've got a contactor. Don't exactly know what that is yet because we haven't talked about it in class, but we'll be using those a little bit going forward later on. So a contactor is just basically an electrically controlled switch that gets a signal, and then with that signal closes a set of contacts or a set of switches that powers something automatically. So instead of us having to flip it on manually, we're able to control it a little more automatically. So you've got contactors on either side of that, basically breaking both legs. And then in the middle, you've got a compressor and a condenser fan motor. And that's a pretty common outdoor unit configuration. Now, the thing that's a little bit different than the way it normally is in what we're going to work with in residential, they're going to show this as a high voltage contactor, meaning it passes high voltage, and then it also has a coil. So the coil, and I know we haven't really shown contactors too much, but the coil is a power consuming thing, whereas the contacts are a power passing thing. So the contacts are made on the top of the contactor, and then the coil's on the bottom, and the coil actually creates magnetism when it's energized, and that closes those contacts, which allows power to go on. So in this case, this is a high voltage coil. Looks like it's 240 volt coil, just like everything else is. So there's no transformer or nothing like that. And then you've got a couple of things in series with that coil, but they're both switches. So in the case of the one on the left, you can look at your reference. That is a cooling thermostat, which just would mean that it is a make on rise thermostat. So if you'll notice the way that that little symbol is drawn, that's just a symbol for a thermostat. And because it's drawn open, means it's able to operate. It's It could be open or closed. And as it heats up, if you can imagine that little switch rising until it meets the other side and makes that switch. And then as it gets colder and it gets cold enough where it wants to kick off, it will be dropping back down to open that circuit up and kick itself off. That also has a LPS, which is the symbol for, this is a symbol for a pressure switch, this little upside down cup looking thing, half circle. That's a low pressure switch. So the low pressure switch in this case is most likely a safety. And the reason I know that, or I'm assuming that, is because it's drawn in a normally closed position, which would mean that most of the time it should be closed and it only opens if something goes wrong. It's not always the case when you're drawing it, but that's the way I would draw that. So that one should be closed unless something happens. So if it were to get pressures too low, it's going to kick itself off instead of running and possibly harming something. So two things that can control that coil, and then when the contactor coil actually is energized, the contacts on the coil or on the contactor close. So you can imagine these things closing, and then that brings on the compressor and the condenser fan motor. I'll show you more about that in class, but that's just a little more in-depth version. So this kind of getting into drawing circuits a little bit, but a little more in-depth version of maybe what we would see more in class in a parallel circuit in HVAC. So, but your calculations, your rules. So just like with series circuits, we had these rules. We had things that were friendly values that we could use everywhere. We still have that, but they're different. So one of the things is that current draw, or I, in the last part was the same no matter where we measured it in a series. In a parallel, that's not the case. So in a parallel, your current draw is going to be the same, or is going to be different on each leg or to each light or motor or whatever it is, because each one is in and of itself its own circuit. Even though they're getting power from the main circuit, it's each getting their own supply. So what that means is that instead of saying I is your friend and all of the I's are the same, in parallel, total current draw equals the sum of the currents in each section. So each section of current, you can add those up, and that would be your total. So I total equals I1 plus I2 plus I3, and however many light bulbs or legs that you have in your diagram. Resistance gets smaller as more resistances are added. Total resistance cannot be added. It cannot be obtained by taking the sum of all resistances like we did before. So this one's kind of weird, and this is probably the hardest one. This is where we have to use some different formulas, and we use one called the reciprocal formula, and I'll show you how to do that in class, but it's a little bit complicated. But if you have a calculator and you know how to use it, it's not bad. So, but resistance gets smaller as more resistances are added. Total resistance does. So you'll do this in your lab, and you'll kind of see a little bit more how it works. But what that essentially means is that R total should be less than. I'm not going to get into the formula too much right now, but R total should be less than any other resistor in the circuit. So by adding those on in parallel, you actually decrease the total resistance, which is kind of strange, but it's the way that it works. Voltage drop. So in this case, E being the EMF, right? The voltage, the electromotive force. Line voltage that is supplied to the load, each one gets its own, and it gets the same voltage. So E should be the same everywhere. So if I've got a circuit that has 4 light bulbs on it and they're wired parallel, each one should have the same supply voltage, which would mean each leg essentially should run at the same, the same voltage, but then it may have different resistances, which causes it to act differently. So E anywhere is E everywhere. So, I was that way in series. That was your friendly value. In parallel circuits, E is that value. So if you find E anywhere, you can find E everywhere. And that'll help you when you're solving these problems. I'm not going to get into combinations. Other than the fact that, like I said, we can control things in series with switches while the loads are in parallel. So that's kind of how we're going to do it. Now, there is a thing called series and parallel combination circuits to where you have loads in both ways, but we're not going to do that. So just to give you a little something to look forward to, this last diagram, this is something that hopefully we'll get to this point in this class. If not, we'll definitely get more into things like this in our, well, we'll get into low voltage circuits in this class, but then when we get into 130, we'll be doing this kind of stuff a lot, and it'll just, after a while, hopefully it'll become second nature to you. So I know it seems confusing now, but the more you see it, the more it'll start to make sense. So don't get overwhelmed at this point. Just go with it and trust the process. All right, so I'm going to skip to this other PowerPoint, pull that up real quick and just see if there's anything else I'd like to add. So there's three rules, three main rules broke down here. Voltage drop across any branch is equal to the source. So E is anywhere is E the same everywhere. Total current is equal to the sum of the branch currents, and the total resistance is the reciprocal of the sum of the reciprocals of each individual branch. Wow, right? That's a lot. Before I go into that, just kind of let that hang there. It's not as complicated as it sounds, but it sounds pretty complicated. So a parallel circuit has more than one path for current to flow, which means that in this case, if this was flowing, each leg would get its own supply, and total current should add up. So, you know, if I have one leg that's drawing 1 amp, another one's drawing 2, one that's drawing 3, then each one of those should add up to be your total current draw. So if I had light bulbs, you know, if I was going to wire a house and I had 10 light bulbs in a room, I would need to add up how many lights I can have on that circuit before I overload the circuit or have to go bigger. So that is really, really applicable because, you know, if I have 10 light bulbs and each one of them is drawing an amp, that's 10 amps. So I can't go, you know, if I have a 15 amp breaker, I can't go all the way to the point that I overload that breaker. So I need to know where to stop. So that helped me do that. Voltage drop is the same, which means that E total would equal the voltage drop across 1, across 2, and across 3, so on and so forth. All right, so I know that not getting into residential wiring much, but this is kind of an interesting point. We have to have a load in every circuit, but you can have a switch on a circuit a plug on a circuit by itself, because if that plug were plugged in, it's going to be connected to a load, and if not, then it's not going to be doing anything anyway. So that kind of an interesting picture of that there. Total resistance. So the total resistance of a parallel circuit is always less than the resistance of the lowest value resistor or the branch. So in this case, your example would be R1, R2, R3 have values of 15, 10, and 30. And if you run your rules and you do your Ohm's law or whatever, you're going to count, well, you do your reciprocal formula. R total is actually going to be 5. Now, how did I get that? Well, you're going to plug those values into this formula, but just for now, look at that and say, okay, if it's smaller, but it's still similar, like if you come up with something that's like 0.2 and the rest are 15 and 10 and 30, that's probably not the right answer. So it should be something similar, but it should be less than. So, you know, this one's 5, the other one's 10, 15, and 30. So that makes sense that that's right. So here's your formulas. And I'm going to go over these in class because this is complicated. So one that you can do that's easy is the middle one, the resistors of equal value formula. So this would be in the case that you had like 3 60-watt light bulbs all wired up in parallel. If they're all the same, and they have the same resistance, then all you have to do is just say the total resistance of the entire circuit is equal to the value or the resistance of any resistor or any bulb divided by how many of them that I have, the number of resistors. So that part's easy. Product over sum, this would be if I had 2 that were connected, only 2. So in this case, if I'm comparing 2 things together, I can do product over sum. That one's not bad, which means you have the resistance of number 1 and the resistance of number 2. You multiply those or take the product and you divide them by the sum, which is adding those. the total resistance of a parallel circuit is the reciprocal of the sum of the reciprocals of the individual branches. This is the weird one. I'm going to show you how to do this in class because it's still a little complicated to explain it. But what does reciprocal mean? Reciprocal means you take a number and you put 1 over it. So 1 over, the reciprocal of 3 is 1/3. The reciprocal of 2 is 1/2, right? 1 over 2. So whatever the value is, you're going to put 1 over it in this, and then you're going to work through this formula to find this value. So here's a realistic answer of that and how that works. So in this case, I've got I've got 150, 300, and 100, and I'm trying to see what my total resistance would be. So you're going to work through that, and you're going to say 1 over the first one equals 1 over the second one. Or sorry, 1 over the first one plus 1 over the second one plus 1 over the third one equals 1 over the total. So when we're in class, when I'm giving you pre-lab info, I'm going to show you how to do this on your calculator because it's really specific in how you punch it in. You can really get kind of mixed up. But once you run those numbers, you're going to come up with a number that's less than any of the others. And so in this case, their answer was 50. And I'll show you how to do that. So I'm not spending a ton of time over that here because I'm going to go over in class. All right, so that's all of that. I'm going to pull up your lab because this is going to be lab 4. Just go through a few little tips on that. Learning modules, parallel circuits. Sorry, lab 4, but it's in module 5 because the first module was safety stuff. So your PowerPoint, parallel, lab 4, parallel circuits. Let's see if this is right. Nope. All right, so it's the same as the last ones, only you're doing parallel. So it's going to give you a few examples. And I'm going to help you all work through these. As like I said, they're a little bit tricky. So you can look through those examples and kind of use that to look back on. It gives you an example here of one that you're going to solve. I'm not going to go through that right now. And then here's your lab. So once you do your lab, you're going to build this circuit. You're going to have a 100 watt, a 40 watt, a 60 watt, and a light switch. You're going to hook it all up and then measure what you're supposed to measure and calculate what you're supposed to calculate. So just like the last one, you have to know the difference between the measured value and the calculated value. So just like on number 3, measure the voltage across each lamp using the voltmeter. So that's going to take your meter and actually measure, the lights are on, you're measuring across those. And then it will say at times, let's see here if I can find an example. Calculate the total current. So you can measure, so it says turn on the power and measure the current flow through the 60 watt lamp. Turn off the power supply. Calculate the total current. So you're going to say, what should it be based on what I've already found up here in these. So, here I found the I of 100, the I of the 40, I of the 60, and now I'm saying what is I total, what should it be? And then you're going to turn your circuit back on and you're going to measure that. So turn the power supply and measure the total current. Compare this to the computed value. So you're going to compare number 16 to what you found in number 14 and see if those are close. And at this point in your lab, when you hook these up, I'm going to have to give you a little bit of instruction on how to wire those up to have enough spots to read all these, because if you wire it like we normally would wire something, you're not going to have enough spots to take all these readings. So if you get to that point and you're a little bit confused, make sure you get my attention and say, hey, you were supposed to show us something here right about when we're hooking those up, taking those amp readings. And it tells you to use the reciprocal formula and solve. So I'll show you how to do that. And once we do it a couple times, it's not bad. Just make sure you have a calculator with you that has square root and square and exponents on it, scientific calculators. So But that's pretty much your pre-lab info in a nutshell. So if you can look through your book, look through any other materials you can find, parallel circuits should be good to go.